Okay, so last time we talked about measurement at the end, right? So again, what is measurement? We claim that for any quantum state, I write it in this bracket notation, which we will discuss later, but now you just take it for granted. This is no difference by writing this as a vector. I should write this as a vector, right? It's just that we want to write it in bracket notation. This is cat. There's some reason that we want to do it. It is a very elegant way to do quantum mechanics or eventually quantum field theory. Anything of any advanced physics will use this notation. And we say for any state, just a state. So just ask yourself, this is not a simple statement. What is the meaning of state? We describe everything in the world by a state, right? Naturally, you say, oh, my state is happy or sad today. But for physical state, it's the same. For example, every one of us sitting here with a certain position, certain emotion at a certain time, that is a state of all of us in this classroom. It's super complicated. You have many zeros of electrons in this room, many atoms that is uncountable, all of them follow quantum mechanics. But for this whole system, it is a state, right? But we also, for something very simple, it also has a state. For example, an electron. It has many aspects, maybe the charge, its velocity, or its momentum, but we also can just zoom in, only look at some property, for example, spin up and spin down, right? And that is a state. We only care about spin up and spin down. Just like as me as a human, there are so many things to describe. Now you can describe me as an old person or a young person, right? So that is a state that we are interested in, and we will only work in that state. So for the states, right, we say that it is a linear combination of the basis states, for example, 0 and 1, because now we assume it is a qubit. Some states has many basis states, right? Here we only have 0 and 1. Physically, it can mean you have an electron spin up. So this can be even say, this is spin up plus beta times spin down. It also can be a state, for example, this is talking about the electron in a left potential well or the electron in a right potential well. Okay, or if you don't understand what is potential well, basically it's just saying that whether this person is in this classroom 341 or in another classroom 343, right? But we are macroscopic object is very spooky if I say I'm in this room and also in that room. But for an electron and quantum object, we can say that, right? And its basis state are in this room and in that room. And it can be a superposition, right? So if it is a superposition, how can you find out whether I'm in this room or that room? What will you do? Measurement, check, and these are all measurement. Open the door, see where I am, right? You may find that this room is empty or the other room is empty, right? So that is what we mean by collapse. And last time we tried to have a wrong analogy, but it's a good analogy that like a coin, you have two basis states, spin up and spin down, head and tail, right? And we say when it is spinning on the table, it's a combination, superposition of head and tail. So if we do the measurement, it will collapse to either head or tail. Just like what we said just now, if I was a quantum object, I can be in this room or another room, a superposition. Then you open the door, it's just like you do a measurement. And then I will collapse to either in this room or the other room, right? So that is the same for a measurement. This is very important because it tells us the limitation of quantum mechanics if you want to get the information, right? I cannot get alpha and beta easily or almost impossible by just doing a simple measurement. But I can do many times to get their probability. So again, it collapses to 0 and 1 with a probability correspond to the magnitude square of the coefficient in front of the basis state. Make sense? Right? So start getting used to this. Okay, so we say superpositions is important in quantum computing. Measurement is special. It limits us how much information we can get from a system. Then another very important thing is the so-called entangled state. Again, you won't understand this completely now, but later you will see it, right? So what is the meaning of unentangled states first? Now, first of all, last time we said that if you have one qubit, how many basis states do you have?
Two.
Two. What are they in this?
0 and 1.
0 and 1, right? And what if you have two qubits? How many basis states do you have? 4. And why do you remember? 2 to the power 2, right? So we make the analogy. We say that in classical computer, if you have two qubits, you might have 0, 0, 0, 1, 1, 0, 1, 1. So for those who forgot about binary number, please go back to review. Or we can review at the end of this class if you have questions. So we represent everything as 0 and 1, right? So this means 0. Maybe let's quickly review what it means, and then you really need to go back to review if you forgot. What's the meaning of this? This means 0 times 2 to the power 1 plus 0 times 2 to the power 0. So this is 0. This means 0 times 2 to the power 1 plus 1 times 2 to the power 0. This means 1. This means 1 times 2 to the power 1 plus 0 times 2 to the power 0. So this is 2. This means 1 times 2 to the power 1 plus 1 times 2 to the power 0. So this is 3. Right? That is the meaning of binary number. Right? Each of them represent the how do you say? I forgot how to say. Right? Just like 99 in decimal or 89 in decimal. The first 9 means you have 9, 1. The second 9 means you have the 8 means you have 8, 10. Make sense? 89 means you have 8, 10 plus 9, 1. Right? And that is decimal. You count by 1, 10, 100, 1000 and keep going up. Right? Binary, it's just that they have different, I forgot the name. Right? It starts from 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So it will be 0. It will be 1, 2, 4, 8, 16, 32 for each place, right? So remember this. So that's why 0, 0, okay, but 1, 1 means what? Means what? I have 1, 1, and 1, 2. So you add them together is 3 in decimal. Okay, yeah, so I know this is a digression, but doesn't matter. It's good to review. That's how I teach. Now, then what? This is classical, but I always say that in quantum computing, then it means you can have a basis state of 0, 0. You have basis state of 0, 1, basis state of 1, 0, and basis state of 1, 1. Right? So this is the basis state of two qubits. Is that clear? Right? We will talk about this later again, but I still, although I say you don't need to fully understand, it's still good if you try to understand now. Now I have a general state like this. So how many qubits do I have? You say 2 qubits? Anyone agree? Anyone disagree? So others are in superposition of agree and disagree. So how can I check if you agree or disagree? Measure, right? So can you tell me you agree or disagree? That's how I do the measure.
I agree.
You agree? Okay, good. Yeah, sorry for that. And can you tell me, right, why this is 2 qubits?
Oh, because
Huh?
So, you have electron one, which is a linear combination of the 0 and 1 basis states. Electron two, which is also a linear combination of the 0 and 1 basis states, has a phase flip on the
Okay.
basis.
Okay, good. So actually, he already know the answer, but he thought that I asked for something very complicated. So that's good. But yes, that's exactly what you say. But he point out one thing. The reason this one confused us for those beginner is that I have 4 terms. I'm kind of confused. So how many qubit? And he point out that this is a linear combination of 4 basis states. Okay, so it's 2 qubit, right? You look at all what I wrote here, they only have 1, 0, 0, 1, 0, 1, 1, and 0, 1. Each of these is a basis state. It is as simple as this one. It's a linear combination of 0 and 1 because this is 1 qubit. Now you have 2 qubits, so you have 4 basis states, so it's a linear combination of these 4. So if we step back, think about 2D, I finish this, a 2D plane, right? The vector is a linear combination of x hat and y hat, and no, it is 2D, right? And if 3D is x hat, y hat, and z hat, then it's 3D, right? So we have 3 basis states for a 3D space, and on your table is only 2D, x and y. Make sense? So it's just like that. Here I have 2 basis states, and here I have 4 basis states. If you feel confused, how is it related to a 3D? Then I tell you, it has almost no relationship. We are talking about an abstract space. It's not something we can touch, but it's a mathematical space we use to describe a physical object. Right. Sorry. This is where it came from. It completely came from me because this is just an example. So this is I try to show a linear combination. I just randomly pick up a state. So it does. First of all, it doesn't need to be half. Second, it doesn't need to be minus or plus. So if I try to make a general case, a general state will be what? Alpha 0, 0 plus beta 0, 1 plus gamma 1, 0 plus delta 1, 1. Okay, and can you tell me in this special case what is the value of alpha? Half. What's the value of beta? Minus half. Yeah, because that is a bracket, right? But you have not learned the math yet, right? So, but it's good. Do you get it? Do you agree? Okay. So I lots of digression, but basically now I tell you I have a 2 qubit state is given by this. This is just example I gave you. Okay. Now, if you look at this one, you actually can factorize it. Now this become more confusing because you have not learned tensor product. We will learn it later. But please agree with me. The operation is just like how you do multiplication. 0, 0 is just like 0 basis state of electron 1 times 0 basis state of electron 2. 1, 0 is 1 of electron 1 times the basis state of electron 2. So you can see I have 0, 0, 1, 0, 0, 1, and 1, 1. So the whole message is that I can factorize it through something called tensor product, which you have not learned, into these 2 states. If you, of course, you don't understand why, yes, mathematically, but the message here is that for this state that I try to describe 2 electrons, right? I just look at them as a couple, right? 2 electrons as a system. Like earlier I said, the whole classroom is one single system, if I want to say that. So you have 2 electrons, I also can say that this 2 electron is a whole system. And this is the state of the electron. And we say that it is actually just a product of electron 1 and electron 2, which means that I can describe the state of electron 1 and also the state of electron 2 independently. I also completely describe the state of the whole system. So how to understand this as an analogy, I would say, for example, like for those who got married, right? Your income and your partner's or spouse income are linked together. If you file your tax separately, to describe your test return for both of you is the same as I just described you, how much you file and how much your spouse file, right? Correct? And so it's not interesting. It is easy to compute. So what mathematician told us that is that if you have a state that is unentangled, they all can be simulated using classical computer efficiency. Now think about that. If you come up with an algorithm and you don't have entanglement, and they all can be simulated by NVIDIA GPU or Intel's AMD's CPU efficiently, do you still need quantum computer? No, right? Because you already find that you can simulate them. You can repeat what a quantum computer do using a classical computer effectively. You don't need that. Okay, so entangled states are not interesting, but there are some states. For example, this one, there's something called the Bell state. Is 1 over square root half 2, and then 0 0 plus 1 1. Now, can I ask you, what is the component of 0 0? Because I said any 2 qubit state can be written as this, right? So what is alpha in this case? 1 over square root 2, thank you. What is beta in this case? Huh? 0. Because it's not there, right? So it is just 0. Very good. And what is gamma? Also 0. What is delta? This is delta. 1 over square root 2, right? So this is another possible state when you have 2 qubits. There are infinite number of possible states. No matter how you try, you cannot factorize it into something like this. So it's just like these two couples now, they file the test together as a family. They're a couple. Now it's very clear to say whether you are helping me to save tests or I'm helping you to save tests. As always, I argue with my wife, right? So because they file together, you get a discount together, right? And they're a couple. So you cannot describe them individually, like how much income I have, and then how much income my wife has, and then you say you can file the total test. You need to consider the entanglement. Not a very good analogy, but does that make sense? Okay, so that is the entangled state. Now, entangled state gives something pretty interesting. For example, the spooky action mentioned by Albert Einstein. Albert Einstein doesn't like quantum mechanics. No, we should not say he doesn't like, you should say he feels quantum mechanics is incomplete. One is that the God should not play dice. He thinks it should be deterministic. Second is this quantum entanglement. So let's think about that. I have 2 electrons, and now I give you an entangled state. I hope now some of you don't feel very confused when I put the arrows up. Because again, anything in the cat notation is just something. Just something have a represent the basis state. It's not any operation, right? So, for example, this is no difference by saying 0 0 plus 1 1. If you mean spin up to be 0 and spin down to be 1. Is that okay? So this is an entangled state. Okay, again, it is given. I prepare 2 electrons in an entangled state. So it's a superposition of spin up and spin down at the same time. How about the component of one spin up and another spin down? 1 0, yes. But do we have that component? Correct, 1 0 or 0 1. But do we have that component here? No. Very good, yeah? Because we don't have that, those 2 components is an entangled state in this case, right? Okay, so I prepare in my lab physically. And then I was very careful. I tried to separate these 2 electrons really, really far away. I start experiment today, and then my great-grandson, eventually at his time, the electron reach 100 light years away, okay? But they're still entangled. Assume that I can do that. That is possible, right? It's just an engineering problem, okay? So what is their state? Still superposition of up, up, and down, down, correct? I just separate them far away. Then I try to do a measurement on the Earth. Now, on the Earth, I only have one electron. It's entangled with an electron 100 light years away. I try to do a measurement on it. When you do measurement, what will happen? Collapse. It will collapse to what? Yes, it will collapse to the basis state, right? Now, if I measure this, then my electron will collapse to either up or down, right? Like what he said. So I have 50% chance to collapse to up or collapse to down. So I don't know which one, but assume that I get up, right? It's possible. Assume I get up for this electron. But once this electron is at up state, but these two electrons are entangled, it only has two possible basis states, up, up, and down, down. So if my electron is sure to be up, then what will happen to the other electron? It must be up, right? Because they're entangled. Because this, just by theory, they have the same spin in each basis state, right? I don't have the zero up, down, and down, up component. Okay? So one spooky action is that I measure the electron to be up, then I'm sure that the electron 100 light years away will be up also. I don't need to measure, I'm sure just by theory. And then this spooky action is like, somehow I do something on the Earth, this information transmits faster than the speed of the light and affect the electron over there. Okay, but this is wrong because it won't happen. In order to show that it's transmitted faster than the speed of light, it means that we show that it violates the causality principle that, we need to show that it transforms the information faster than the speed of light. Then it will violate the causality principle. Like I can go back to the past and do something. Do something to affect the future. But you can show that you won't be able to do that. Yes.
State will be known.
Yes.
How does that violate causality? I mean,
No.
Causality.
It won't violate. Eventually, cannot use this to transmit information faster than the speed of light. It's just an impression. But what I'm trying to say is that you measure something on the Earth, it looks like I will know immediately what happened 100 light years away. You don't need to even to measure on this second electron. I know that it is already spin up. If they are entangled, then I know that what happened to that one. But this one is not really the reason that Einstein doesn't like, because he cannot prove that this is transmitting information faster than the speed of light. But it is actually violating the Heisenberg uncertainty principle because, but you have not learned it, so I will be fast. We'll look at it quickly. Because when I measure it to be up, then I'm 100% certain the electron in the other planet is up. However, the person on the other planets can measure in another so-called orthogonal basis, left or right. And he can measure it, then it will become left or right. And 100% sure that it is left or right. Now then, this theory has problem because based on my measurement, it must be up, 100% certain. But that person over there measure left and right, also 100% certain whether it's left and right. But in Heisenberg uncertainty principle, you are not able to measure both of them precisely at the same time. So this is very confusing. So you might not understand now, right? But so don't worry. But you do see something like spooky action, the important thing about entanglement. And you can start thinking about it. And you even can think, is it really so spooky? I buy, let's say the Safeway only sells 2 types of gloves. One is red, one is yellow. And I'm colorblind. I go to Safeway, I pick one. And then I send one of them to my friend, let's say in Japan. And I'm colorblind. I even don't know what color I have. My friend opened the box and my friend knows immediately what color I have. So there's something like this in classical already. So you need to be careful, right? So you can think about this philosophical debate, but doesn't matter. The point is just have a feeling. Yeah. If you continue to measure instead of using the basis either up and down, right? Magnetic. So to measure, you actually need the magnetic field. Then it will always be up, right? Just like the coin, you collapse to head, then you keep hitting it, it's always head. Yeah. Yes, then now no more entanglement. So what she's trying to say is now you only have to stay up, and no more entanglement. But because you collapse to the basis state, so so you know what will happen. That 100% you know what will happen if you measure it again. Okay, good point. So whenever you do a measurement, you will collapse to the basis state. Then nothing interesting will happen. However, you can measure in another basis. Then this one become a superposition of in another basis, which we will discuss later. So that is a good point, right? Then so it won't be always at here if you try to measure in another basis. Okay, good question. Yeah. Yeah, you need to manipulate it so that 2 bodies will entangle with each other. Yeah. Okay, so just a feeling, right? Then you know what we are going to study this semester. We are going to go through the math and have a deeper understanding. So we say superposition, measurement, entanglement are very special in quantum mechanics, and they are used in quantum computing. And then now let's look at what a quantum gate, right? So in classical semiconductor, what is a gate? It is just transistors. Now a NOT gate, you have a NMOS and PMOS connected together, right? Anyone doesn't know what is a gate? Classical gate? Okay, you all know, right? But how about quantum computing? So we say that we have, let's say, electron, right? Many passive quantum objects. It can be electron spin, electron in this room or that room, right? Or it can be a superconducting quantum computer. It can be a trapped ion with different electronic energy level as 0 and 1. They sit there, and you know it's very difficult to solve. However, they are very boring. If you don't apply anything, the wave function is there. Yeah, it is very complicated, but just boringly complicated, right? Just some wave function. So what do you mean by quantum gate? Quantum gate is nothing but just to change it from one state to another state. Okay, so there's something called Bloch sphere, which we will not go into detail even at the beginning. We wait almost until the end because this one is a little bit confusing. But now you can take it for granted is that if you have one qubit, the state of that qubit will be mapped to a point on the surface of this Bloch sphere. For example, if your state is 0, it's at the North Pole. If the state is 1, it is at the South Pole. If your state is 1 over square root 2, 0 plus 1, it is on the equator at this point. And if your state is 1 over square root 2, 0 minus 1, then it is on the opposite side of this equator. Is that okay? And anything, you just give me any number, any superposition, it will be a point on this sphere. So that is the first thing. Now, as I say, what is quantum gate? Quantum gate is to change a state from one state to another state. Then it means to rotate a point on this Bloch sphere to another point of this Bloch sphere. So that's why you have heard people talk about the quantum computing is just rotating the state, right? So you can think in this way. But what is the meaning of the Bloch sphere? We will discuss at the end of this semester. Just want you to be very careful, not treating this as a vector, right? Because if in a real 3D space, I have a north pole and south pole vector plus z hat minus z hat, when you add them together, what do you get? 0, nothing, right? Z hat minus z hat equal to 0. But here is not the case. 0 plus 1 is what? Just a state, a linear combination of 0 and 1. Turn out to be on the equator, right? So that is the confusing part, but we will tackle that later. But for now, you just agree, the so-called quantum gate rotate the vector on the corresponding hyperspace, okay? You're rotating that. Because of that, you can rotate forward, you also can rotate backward. And what is a gate? And because of this, we are modifying the state. For example, you are just trying to modify my emotional state, happy and sad. Or you give me more money, I become happy. You take away my money, I become sad, right? So I don't need to move physically to go through this process. It's how you operate on me. So it's the same for this laser pulse, right? You shoot microwave pulse and laser pulse to the atom, to the electron, to whatever Josephson junction, then the state of the object will change. And then that is a gate by itself already, right? So in silicon, you may think Intel say, I can put 10 billion transistor on this 2 cm square, 3 cm square wafer. If you ask them to put 1 trillion, they'll say, oh, I cannot, we need a larger chip, we need a smaller transistor. But for quantum gate, what you mean is that you say, I need 1 trillion gate, all you need to just shoot the laser pulse 1 trillion times. Okay, so you don't need to worry about, oh, man, I need a very large real estate, I cannot afford it. So that is the difference, okay? So some gates have classical counterpart, like NOT gate. In classical circuit, you NOT 0 become 1, NOT 1 becomes 0 here, NOT 0 state, basis state become 1, 1 basis state becomes 0. We will discuss this in the future carefully. There are also something called C-NOT gate, control NOT gate. So this is what can be used to form entanglement. He just asked, does the electron already entangled or you need to make it entangled? It can be entangled or not, but usually in quantum computing, we'll initialize it so none of them are entangled, they are all at ground state. And then you apply some 1 qubit gate and a C-NOT gate to make them entangled. Right? Then you have an entangled state, you continue the computation. Some gates doesn't have classical counterpart. For example, Hadamard gates, we'll learn that later also. Apply H to 0, it becomes 0 plus 1, a linear combination. Right? In classical computer, if you have a register, you have 0, then okay, fine, or 1, fine. But you say, oh, it can be 0 or 1, then you say that's an error. Yeah. Okay, so actually it's exactly here. 0 plus 1 will be at this point. 0 minus 1 will be at this point. But we will learn why in the future. And I can tell you more. For example, this part is 0 plus I1. I is the square root minus 1, the imaginary number. This part is, this point is 1/2, 1 square root, 0 minus I1. And then for any point elsewhere, they can be very weird number. So any state can be mapped to here, up to a phase difference, which we will not discuss now. But basically, you can think of any state, I can put it at a certain point of this Bloch sphere. Okay, good. Yeah, so then what he's saying that, okay, if I have a state on top of the North Pole, I apply the Hadamard gate, it will rotate it to this point. Okay, yeah.
The CNOT gate you said can be used to entangle.
Create entanglement. Yeah. So here is the CNOT gate. We will not discuss its meaning now, but there's another thing about quantum gate we need to realize. This is a classical LAN gate. If I tell you the output is 1 and it is a LAN gate, are you able to deduce the input? No, because 0, 0 will give me 1. 0, 1, 1, 0 will also give me 1. So this is not reversible. Classical computing is not a reversible computing. Irreversible computing consume energy, so they always generate heat. Now, how about this one? I tell you this is a CNOT gate, and if I tell you the output is 1, 1, are you able to tell me what the input is? Yeah, based on this, you see that it has a unique 1-to-1 mapping. Okay, so quantum computing is reversible. So although we know we need a lot of energy to cool down the quantum computer, but quantum computer itself does not consume energy because it's just like because it just follows the Schrödinger equation. So if there's no friction, no dissipation, right? Just think about, where I'm rotating a ball in the space. You rotate left, rotate right, you don't consume energy if you do it slow enough, right? So that is the first thing. Why this is important? It is that it is like if someone tell you that he or she invented a new quantum gate can solve every problem, and then you find that it's not reversible, then you put this in your project, I don't need to look at it, I will just give you 0, because I know you must have made some mistake, because every quantum gate needs to be reversible. Okay, so now if you think about the rotation, it makes sense also. A quantum gate tries to rotate the state on Bloch sphere from one point to another point. Oh, then of course I can rotate it back, just applying an opposite, the inverse operation. Right? Make sense? And then here I try to emphasize again, so-called a quantum circuit is you have a state, you're sitting there, and then you apply a gate, which is a laser pulse or microwave pulse, you keep adding to them. Anytime you want to go back, you can go back to the original state, but just by applying the inverse operation, unless you do a measurement. Once you do a measurement, what happens? The wave functions collapse, right? Then you cannot go back. Okay, so this is more like a flow. I just talking about typical one, the flow of time. But when you go to photonic qubit, it's a little bit complicated because the qubit need to travel. You cannot stop light from traveling. Yeah.
So the moment you
Yes. Well, I would say the moment you measure it, the state is not reversible, right? Of course, you can apply the corresponding reverse quantum gate, but it won't bring you back. Yeah. Exactly. That is another reason why you see that the input and output are the same. So that is something later we will see when we design something called quantum oracle. You need to make them to have the same number of input and output. Good point. Yeah. Okay, good. So let's talk about the implementation of qubit. Sorry, someone keep calling, just make sure it's not urgent. I'm sorry. I don't want to. Okay, it's spam, so don't want that some hospital or whatever. So so what can you do? I can use, and actually that's one thing. So we try to see how to introduce quantum computing to high school, middle school, or even elementary school student, right? You need to find some analogy. But you almost cannot find anything classical to talk about quantum computing. Although some people come up with something still not very nice. So that is because we really don't have classical thing that has one-to-one correspondence. The only thing I can think with the best is the mood. There is really something superposition because there's no physics with your mood, but I always can say that I'm in the superposition of 40% happy and 60% unhappy. I guess you have the same feeling also, right? But of course, you cannot use to implement this, is just a joke. So what are the possibilities? For example, you can use spin. That is what we usually heard of. So electrons spin up and spin down. We have different energy if you have an external magnetic field. Okay. So and I actually forgot. I think when it goes, if the external magnetic field goes up, then you have lower and higher energy. Yeah. So because spin up, if the electron, the magnetic moment will be spin down. And then you have negative mu dot B. Yeah. So just can ignore me, sorry. We'll talk about that in the future. But basically, if I have applied external magnetic field and I confine the electron in this quantum dot, so-called quantum dot, right? Just a potential well. You don't need to really understand, but you can understand it as a box containing a particle, right? And spin up, spin down, I have two different levels. And then the electron actually can be in a linear superposition of these two states, either spin up or spin down. Okay, you agree or not, this is the physics. Okay, it's a superposition. So that is one possibility. This one also very interesting. Photonics. This is called, we call it dual rail encoding. So what does it do? You actually have two optical paths, let's say fiber, optical fiber, or a waveguide on a chip. You shoot a photon, one photon into here. So you have some probability of going to the upper path or some probability to go to a lower path. From wave mechanics, probably you can understand, I shoot some wave of light to the junction. You will expect some of the wave will propagate to the upper path, some will propagate in the bottom, right? Make sense? Or water pipe. You have two pipe, two outlets, your water wave comes in, you will feel that some energy will go up, some will go down, right? Do you agree? You don't? Or no? Or you have a river, right? You have a river, and then you have two branches. And then you propagate some water wave. Isn't that you will feel some will go up, some will go down? Right? But this is classical, and you may actually able to calculate what percentage will go up and go down. But now, same for a wave, for EM wave, you have the same condition. But what if I make it so weak, so you only have one photon? So now we're talking quantum mechanics, right? Even light is a particle. This is one you to accept it if you have not learned that before, right? So you can count how many photons. So now, this photon can go up or down, but you don't know where it goes. You only know the probability based on your strength that you calculated. Right? Yeah.
So actually, in the diagram, part 1 and part 0 had to be like connected.
Yeah. Sorry. So this is I just copied from a paper. So actually, these two are connected, and then I shoot the light inside. Yes, just like the river. Sorry. Now does it make sense if I connect it?
Yes.
Okay. Yeah, but doesn't matter. The point is, if I don't look at it, I tell you that it can be a linear combination of the light is on the top path or on the bottom path. And that's why I have alpha path 0 plus beta path 1. Okay. How do I know where it is then? Measurement, yes. So I will have something maybe called single photon detector. When a light go into it, you will have an electrical signal pulse coming out. So if I put both here and I see that there's a pulse coming from the upper part, I should not see another pulse from the bottom, because I only have one photon. right? If you get 2 photons, then that's a problem. And there's a measurement. And what? Wave function collapse. It collapsed to upper or lower path. And again, it collapsed to the basis state. So no matter how you encode the qubit, the point is once you measure, you will collapse to the basis state. Here you will collapse to either spin up or spin down. Here when you measure, you collapse, you find the photon either on the upper path or lower path. Yeah. What do you mean by same property? Yeah. Yeah. Right. So good point. So he said, regardless of the medium, do all these qubits share the same property? We should say they all need to have the same property required for quantum computing, and that is the so-called De Vincenzo's criteria. They need to meet those 5 criteria. For example, like what you said, we should have an entanglement gate. We should be able to make them entangled. If you come up with a technology, everything is perfect, but you are not able to make it entangled, you cannot make a good quantum computer from it, right? Another night you should be able to measure them individually. You should be able to. They should have a long decoherence time. They can be initialized easily, and they have 2 levels, right? These 5 criteria. But do they have some properties that they don't share? Of course, because they're different systems. However, those are not the necessary property to have a quantum computer, right? Okay. Yeah.
Or 2 electrons for that.
Yeah.
In this case, you only have 1 electron. What is it entangled?
No. Here we only have 1 qubit, so no, we cannot do any entanglement. So if you want to have entanglement, then I need to add 1 more electron here. So here it looks like 2 electrons, but it's just saying that if the electron spin up is at this level, spin down is at this level. Yeah, so as you can see here, right, only 2 basis states, 0, 1, right? Same for here. So now if you try to add 2 more paths, then you have 2 qubits. And then you try to bring the waveguide together, then you can start have something like that. Yeah, good question. Right. Another is so-called superconducting qubit. We won't go into detail, but basically it's like we have something called Josephson junction. It's just like an inductor. And combined with the capacitor, you can form an island. And in this case, it's not the commonly used what we call transmon qubit, but let's just use something called charge qubit. The reason is that I want to show you that the way it encodes is that if I have an extra pair of electrons, we call Cooper pairs, here, then it is 0. If we have 0 extra, then it is 0, state 0. If you have 1 extra, then it is 1. This is just like saying that if there's no extra person in this room, then we have a quantum state of 0. If there's 1 more person comes in, then we have a quantum state of 1. And the superposition is a superposition of whether that person comes in or not. Okay, where 1 person comes in. So now we're in state 1. Do you understand what I mean? So here to show you that, okay, the basis state is spin up and spin down. Here to show you that the basis state is the photon is on top or in the bottom. Here the basis state is that I have 1 extra pair of electron or I don't have 1 extra pair of electron. And then they all can form superposition. And that is 1 qubit. Yeah.
Right. How many ways have been invented for the qubit?
About 7 possible ways, right? Spin, photonic, superconducting, trap ion. You trap the ion in space, and then you laser to process the electronic level. Neutral atom, you actually use laser, something called laser twister. You can put the neutral atom in space, and then again you process it with laser. Majorana, fermion, that Microsoft announced this year generate a lot of interest, but that is the slowest because if they even don't have a system yet, I mean, just starting having the first qubit. But if they're successful, they can come up very fast. And then vacancy defect pair in diamond or in solid state, and some others. Yeah.
You need to change the way I mean, depending on what you're computing, I guess you have to do different photonic operations, right?
Yeah, you do need to have the so-called 1 qubit and 2 qubit gate. So this we won't cover in this class. But yes, you use waveguide, beam splitter, Meissner interferometer, etc., to do the 1 qubit computation.
No, what I was asking is, do you have to literally need different hardware, if you will, for different computation?
Yes.
So how?
So the point is this: photonic is also a little bit tricky because you will have different hardware. You need to control the photon first. You need to generate single photon, guide them to the right path, do the interference. But nowadays, the most famous company is called Psi Quantum. Is in Palo Alto. I hope that some of you can get a job there. Yeah, really. I mean, we're well qualified. Job doesn't mean that you really do the hardcore optical computing if you are not interested in it. You will see that you need a lot of electrical engineering, all those control signal. So they do something called measurement-based quantum computing. This is a little bit interesting. I don't understand well neither. So to do quantum computing, besides applying gates, you can also make them entangled. You have many qubits, you entangle all of them in a certain way, and then you do measurement. You measure a special measurement. You do a special measurement, and then based on the result, you do another measurement in another basis or on a particular qubit. You keep doing this, eventually you will get the answer you want. That is called measurement-based computing. And the name that they are using is called what? I suddenly forgot. Fusion-based computing. Yeah, fusion-based quantum computing. So it's a part of measurement-based quantum computing. Now, although I don't know the math, but this makes sense. Think about this. If you want to get information from a person, right? That is actually a computation in some sense. Because you're a physical object, right? I try to get some information from you. I actually can use you I can do computation to get information. How do you get information? You can ask different things. Right? How are you today? Who's your parents? What are they doing? And eventually they find out you are a billionaire, right? But they don't ask you whether you're a billionaire, right? So that is possible. Of course, this is very hand-waving. But yeah, so that is one thing, because that make it also more fault tolerant. But I don't have much information. Yeah. So, okay.
Yeah, I was just curious. I mean, how can you? I mean, are the quantum computers mass manufacturable? You have to constantly change the hardware for every.
No, this one you won't. I mean, you still need to reuse the hardware.
Okay.
For some of them, right? Because that is the point. For every quantum computer, there's something called native gate. Because for spin qubit and superconducting qubit, they have different physics. For spin qubit, maybe I can implement something called control phase shift gate easier. This one I can implement I-swap gates easier. Both of them are entanglement gates, and they can be converted to C-NOT gates by adding some 1 qubit gate. So it really depends on the physics that you have. Yeah. And then all these native gate will form a universal set of gates. So once you have these few gates, you can construct any quantum computing circuit or approximate any quantum computing circuit reasonably well. Okay. Yeah, a lot of information. Now, another thing I want you to pay attention to is that this is not a hardware class, but still to understand. And that is the very reason why quantum computing is still not successful yet, is because they can lose their state due to noise easily. And this is easy to understand. If you look at this separation, we are talking about micro electron volt, or the temperature is just in the order of how much degree. It's like 0.02 Kelvin or 20. Is that though? Yeah, 0.0 Kelvin. That is very cold. What is the thermal energy of room temperature? 26 millivolt. Okay, 300. So at 300. So you cannot, most of the time, you cannot operate quantum computer at room temperature, except photonic quantum computing or trapped ion. But they have some component we need to cool it down to very low temperature. For example, photonic, you need the single photon detector that I mentioned earlier. Very often, you need to do a lot of measurement, and you need to cool it down to 4 Kelvin. So the one reason photonic might be very successful is that they don't need cryogenic dilution refrigerator. But for spin qubit, superconducting qubit, you see that we need to bring it to dilution refrigerator temperature. So I was wrong, right? This is not the, this is the energy. Yeah, that is the temperature. This 0.23 Kelvin, and we need to bring it to 10 millikelvin. Yeah. No, because we want to reduce the noise due to thermal heat. Yeah. To reset them, actually this, and then this one, when you bring it so low, you can separate 0 and 1 clearly. Right? Imagine what is thermal noise. It's just like vibrating, right? So let's say I'm on a double deck bus. I can be on the first floor or second floor. You can see it if I'm on a very stable road, right? What if there's a super earthquake? Then even I'm on the first floor, you actually don't know whether I'm on the second floor because the vibration, the noise is more than the separation between the upper and lower deck in that sense, right? So that's why you need to cool it to very low temperature. There are two types of decoherence time. One is that you can, if you're in excited state, right, higher energy state, you can decay to ground state. This is very easy to understand, right? We all know that if you lose energy, you go to the ground state. And this is the so-called T1 time, or called energy relaxation time. Right? For example, for superconducting qubit, it can be in the order, like say 200 microseconds. The second one is what? It's not really losing energy, but you see the phase is different. Now, this one is a superposition. It was 0 plus 1. But because of noise, eventually we don't know is 0 minus 1, 0 minus I1, 0 plus I1, or whatever. Now, but that is very important because at the very beginning I say we use interference to do a lot of algorithm. Once you lose the phase, you lose all your information, right? So this is called T2 time, and this is called dephasing time sometimes. There are many names. We will talk about this at the end of the lecture when we talk about the hardware. But actually, I don't know if I want to talk about hardware or quantum error correction, but we'll talk about this a little bit, right? So just remember that the reason it is not successful yet because we have very short time. And that's why we need fault-tolerant quantum computer, and which we means to apply quantum error correction to it. But how do you apply quantum error correction? We are going to learn and prove this theorem. That the first theorem is no cloning theorem, means you cannot copy a quantum bit. Okay, a general bit. So now you say, I have a bit which is alpha 0 plus beta 1. I don't know what it is, but I want to copy it. You cannot, right? Just like if someone copy the homework from the others, it's okay, you don't know what it is, you just photocopy and then you can submit, right? That is completely different. And why is that? Because in order to copy something, you actually need to do measurement first. And once you do measurement, the wave function will collapse. Okay, so there was something later we will learn, quantum teleportation. You can copy. You can copy something from electron here and suddenly to an electron on the moon. But the copy on your hand will get destroyed. So you did not copy. You just transfer the state from your hand to the electron on the moon. Okay? Instead, you have two copies, one on the Earth and one on the moon. Yeah.
When you say you do the entanglement, the
Yeah.
two
Yeah.
one qubit will have the same kind of that can be considered as a copy.
No, that is a very good question. So is this maybe I just don't go back too much. Click. Is this a copy? No. First of all, I did not do any copy. This is just I create an entanglement. I did not really copy an information that I don't know and to there, right? You can say that you make. First of all, this is not like two separate states. First of all, so it's not a copy of each other. Although you can say, if we don't consider entanglement, they are the same as each other because they have the same. That is fine. But you are not doing the copy action. You are just creating two things that are the same if you treat this as a copy, right? Okay, no classical system now. So now you go to error correction. So in classical system, let's say I want to transfer something to you. I call you. I want to tell you something. I say 1. But it's very noisy. My signal got distorted. What will you do? You say, can you say again? I say 1. And if you still cannot say, I'll say, I can say 100 times. And then you decided maybe, 70 times I heard 1. I think it should be 1, right? And that is the so-called classic error correction. You used this, I certainly forgot the name. What do you call this? Repetition code, right? You repeat it. Instead of transferring 1 0, you transfer 3 0. If you only have 1 bit flip, the probability of getting error is pretty low if you transfer more data, right? But you cannot do this in quantum computer because I cannot copy. So I cannot send many copy to you. Make sense? So that doesn't work. You cannot have repetition. But there's something similar that people are really smart. They call syndrome measurement. And I will understand as this. Like I have fever. So is it a regular flu or is COVID, for example? I was thinking, well, if the doctor is super experienced, the doctor maybe doesn't need to probe my arm to take the blood to do whatever test. Let's say we don't have this rapid test, right? Just look at my temperature, how fast I breathe. This syndrome, maybe he already can tell me that I have a regular flu, right? So why? Because the syndrome is correlated to the virus you have. And that's what people do. So I have this qubit psi. That is the information I have. But I cannot measure it because I measure it, it will collapse. I just want to transmit this information to the other place. But you have a noisy channel. And what I do is I entangle it with some auxiliary qubit, making correlation of this qubit with some junk qubit that I don't need eventually. And then at the end, I try to measure those junk qubit. Based on the measurement, then I will know what happened to my qubit. Maybe my qubit got flipped, or my qubit has a phase change. But I don't look at my qubit. All I need to do is just apply the correction to qubit, right? Just like the syndrome measurement with the doctor, right? He measured the syndrome. He doesn't look at me. Okay, you have regular flu, take this medicine. Or you have COVID, take this medicine. And then I got recovered, right? So this auxiliary qubit is a very important concept in quantum computing. Not just in error correction. We always will borrow some qubit, let it help us do something, indicate something, and then we dump it. So very, very inhumane, but they're very important. And finally, you will get the answer you want. Okay. Yeah. You don't. You only know what happened to the psi state. Because, you know, it's just like this. Let's say the first one is, the first one be, I mean, Okay, so this is something got you confused. When we say entanglement, it's not limited to this. Entanglement can be very complicated. It's not always 0, 0 plus 1, 1. So it has many other possible states. They are still entangled states. And when we're talking many qubits, it's not that straightforward. Yeah. So entanglement doesn't mean that we make it into here, into something like this. Yeah. So you cannot know exactly what that state is, but you know what happened to that state. Okay. They measure what? Say again. Other than spin of I mean, just the state is not 0, 0 plus 1, 1. When you have entanglement, it can be 0, 0 minus 1, 1, 0, 0 minus I 1, 1. Yeah, or not the same ratio. Yeah, and also there's some fully entanglement, partial entanglement. There's something you can calculate. So it has something called entanglement entropy from 0 to 1. The degree of entanglement is continuous. Yeah. Something are super entangled, some are partially entangled. Yeah. So what I'm trying to say, just do not think it is only this. Yeah, if this is only this, yeah, you measure one of them, you know the other. But spin is just a way to represent the qubit, right? So this can be optical path 0, optical path 1. Yeah. Okay, so one very important message I want to say is quantum computing, you have a lot of information, right? But do not think that can replace classical quantum computer, because now we learn about measurement. There's no way for me to efficiently find out what A0, A1, and A2 to the power n minus 1 are. If I can find that easily, then yes, it looks like I can replace anything. But since I cannot do that easily, I use constructive or destructive interference to get the information I want, right? Such as if a function is balanced, and what's the period of the function? And that we will learn in this class. And so definitely we should really know that you cannot replace classical computer, but you'll be a very powerful accelerator. So today I saw LinkedIn, there's a post linked to IBM's announcement. So IBM and AMD are forming a joint effort or research to do something so-called quantum-centric supercomputing, something like that. What you mean is, you try to harvest IBM's quantum computer and AMD's CPU, GPU, FPGA to form two very closely connected systems, so that the quantum computer can use to optimize something that the supercomputer cannot do well, and the classical computer will be used to help to analyze the data from quantum computer. So they have a lot of read-write interaction, right? So you have a supercomputer, you can do the real-time response very fast. So as I said, even for this quantum error correction, you need to do a lot of measurement and keep doing measurement, because you have defacing every 200 microseconds. You need to maybe keep doing this every 10 seconds or 10 microseconds or whatever. That need a lot of computation. Okay? Any questions? So pay attention to this. Yeah.
There's so I mean, like you said that you do the aircraft, but you can't copy. So how do you? But once you measure it, you can copy, right? That's my understanding so far.
No, you don't really measure, because I do something to entangle with you. Okay? Let's say you have a friend, right? You are so good with your friend. When you're happy, he's happy. When you're sad, he's sad, right? So like entanglement. So now I really don't need to talk to you, right? Let's say I'm your father, right? You're annoying, don't talk to me. But of course, I always look at your friend's Instagram, or if he said he's sad, then I know that you are sad. Something like that. I don't need to talk to you, right?
But then how do you get the results out of the? Yeah, I'm not fault.
No result here, just to preserve the qubit. I'm not doing any computation.
Oh.
And then I find that, you got flipped by a gate, then I try to flip it back. I know that because based on the ancillary qubit, I know that you got flipped. So I will apply a quantum gate to correct it. Then you will be stay as before. Okay. Okay, yeah, I did not go into detail, but this is just an error channel. It means that I inject some error into this one, and then we may flip the qubit. This error, E means error. You try to imitate a communication channel, which inject lots of error. Yeah. Yes, if you ask the qubit, you can't. Because I want to preserve this qubit for computation. Then it becomes 0 or 1, then I cannot use it for computation. This is still in the middle. So two things. This is actually a quantum communication channel. I want to send the qubit to my friend in which there is some information. They might not just measure it, they actually use it to do other computation. For example, with the state of the qubit, they might be able to decode some secret code, right? But they cannot look at it. So they need to error correct it. And I later this is just a continued quantum computation. Again, this is what this, if you're quantum computing, this is just the time. I just keep the qubit just sitting there, but now you get noise. I correct it, and because later I am going to do another computation on top of it. For the rest, I know a little bit slow. I thought that I could finish early, but it's a very good discussion. These are not very important. I will have resources. I have this this you can try IQM Academy. They talk about quantum computing. NVIDIA quantum computing. This is just emulation. NVIDIA put a lot of effort to use the GPU to emulate quantum computer, and maybe can also solve some being some interface. So you can take a look. So although they don't have their real quantum computer, but they have a lot of education and research effort in this area. And of course, we have quantum IBMQ. I put a video on the YouTube list to tell you how to create an account and use their quantum computer, right? These are just we already cover, and this just some map, a little bit old, but you can look at the landscape, and some of you really want to go to this industry can target this company and tailor-make your career for that. I just spent a lot of time on realization already, so I think that's it. I want to give the time back to you. Any questions for